The user interface is somewhat simple, but it's very powerful. So in this case, it says that this membrane builder for ChamGUI defines the Z axis as the membrane normal, which is something that is common, and Z equals 0 is basically the center of the membrane bilayer. So we need to make sure that the protein is correctly oriented. So in orientation options, it says there are 4 options. We use the PDB orientation because most of the time the proteins are oriented in the Z axis, so that's why. And then it says here that you may need to be careful when you do this and check your structure. Otherwise, there might be some errors that you may not catch up until the end of your setup, and even you're doing your simulations, and it costs you a lot of time. You can imagine that if the protein is not aligned correctly in the membrane, you may need to equilibrate or do a lot of simulation just so that you go back to the correct place. Okay. So in this case, we leave it like that. We just go next step. There might be some warnings popping up, but you don't need to worry about that. It's basically what it's doing is, okay, so great. So in this step, we can view the structure. So let's do that. And this is a cross-sectional area of the protein. So you can tell that some part of the protein, this peripheral part is in the intracellular domain. So let's see what it shows the protein. Okay. Yeah, so we are here in this figure 4, where we shows the protein orientation and the X and Y planes of the membrane are here in the here. So for example, we can rotate and show that the orientation is correct. We have the barrel here going across the membrane, okay, and the peripheral part here. So we can trust this setup here. Okay, so let's see. So the next thing is it shows here is we can generate the water, the pore in the membrane, and here we are in the area calculation, and let's see if it says if it shows what it can. So here we have the option to select whether we want a membrane that is homogeneous, basically the same lipid, or heterogeneous. So basically, there are different ways we can define the type of box. Okay, usually people do rectangular boxes because those are like I think are more efficient in terms computationally, but hexagonal boxes are supported for ChamGUI and also for NAND. And then basically the other options are regarding the water thickness that we can see here. There is a figure in the tutorial, figure 6, that tells you that this thickness is basically the empty space, how much empty space that is gonna be populated by water do you want. And this is important because if you imagine that this is this simulation has periodic boundary conditions, so you want to have some cushion of water between the replicas. So you can imagine that here, if the box ends here, then at the bottom here you have the second replica. So you may, if the distance between the protein and the replica and the protein in the replica is too small, then there could be some problems given by this interaction. Okay, so you may want, always you want some, as I said, some cushion so that interaction is small. And this is defined by this parameter here, the water thickness. Okay, so this is 22 angstroms. I think it's okay. I think I've seen people do more. Something that you can imagine that the more thickness you add, the better your system will resemble something like an actual system. But the problem is that the more water you put in the system, the more atoms there are in your simulation. So therefore, the most it's gonna be most demanding computationally. The more atoms you have, the more it will take for you to simulate this. So there's a trade-off between how much water you want in your membrane simulation, so that the interaction between the replicas, the periodic boundary replicas, is minimal, but also you don't want that much water, so that you don't need to compute that water in without because water, most of the time, water doesn't provide any information from your system, just there to as an environment. Okay. All right. So, and here, in this part, you can play around with different lipid compositions for your membrane. So I think some of these more complex lipids like cardiolipins and cholesterol are something that has been recently implemented. Okay, so let's see what the tutorial asks for us to do. Okay, let's see. So go to the lipid type column here, and in CL, which is cardiolipin, where is cardiolipin? CL here. Set PbCl2 a slower leaflet ratio. So this is the upper leaflet ratio and lower leaflet ratio. So you can define, this is something that you can define. You can define different type of leaflets. The upper leaflet can be one composition, the lower leaflet can be different compositions. So that is given by this interface. So it says, okay, let's go to this one, PbCl, and let's go to the lower leaflet, the second column, and let's put a 2 here. And then in bacterial lipids, here it says set the lower leaflet ratio, or PMPE and PMPG to 818. The following is PBPE. PBPE is this one, 8, and then PBPG is 2. So the idea of this is that you may have information about the conditions, real-life conditions of your protein. Basically, depending on the tissue your protein is, the cell tissue your protein is the membrane can be different. Some tissues or some cells have more. For example, in this case, this is a bacterial membrane, so it has a more predominant composition of these lipids compared to other membranes. So this is coming from the experimental information about this particular membrane in this particular cell. Okay. Okay, so I'm not gonna go over everything because it's a little bit repetitive. So, but and I don't wanna bother everyone that it's this is a very particular case. This is an LPS lipid, which is something that contains a lot of sugar molecules. So let's imagine that we did already that, and then we can go to the next step. Okay, show system. Okay, so it tells you here that based on the ratios that you gave, this is gonna be the lipids that you have. So since we didn't fill any most of the, let's give me an oh, because I didn't select any upper leaflet lipid, right? That's the problem. So what was the so I need to select something in the, I need to put a number here in the upper leaflet, otherwise there are no lipids selected there. So let's select something. Okay, sorry. Okay, so it says that in LPS, I want LPS to be 1 in the upper leaflet. That was the thing that I was missing. Okay, so if I do this, now I click here, and it's gonna show that only the lipids that are present. So in the there is LPS in the upper leaflet, nothing in the lower leaflet, and then we have sorry, didn't like what I selected. I did select lipids in the lower leaflet. Okay. It's kind of like it's giving me error with the lower leaflet. I don't know why. Let's do it. Let's make it a little bit more simpler. Maybe I can change everything to 0 and make it a different type of lipid. So let's do BOPC. Put a 1 here. Let's see if it works now. Okay. Give me some errors for the lower leaflet. I don't know why. Let's see. Let's go back to the tutorial. Okay, maybe I need to add some initial guess for the length of the membrane patch. Usually, this must be some number that so that the protein again doesn't have interaction with their periodic replica. So you want the number. So that's basically we are talking about this this distance between the in the X and Y. So usually people do around like 100 and 100 angstroms. That would be like a reasonable number, I think. Let's do 75 so it doesn't take too much to that fix. Okay, so that fixed the problem. It was complaining that I didn't give any length, and of course it cannot produce a membrane if I don't give it some details. So now you can show that I have in the lower leaflet, I have POPC because I fix everything that I did back to try to find the error. And on the top, I have this LPS, okay? So, and then it gives some of the details of this tentative system. So for example, you can tell the area of the protein versus the area of the versus the total area. So you can tell it's okay. It's like a quarter of the total system. A quarter is a protein. Could be a larger membrane maybe. And this is the final values of I think of the protein. Okay, so let's do next step. Let's see what's the issue. The system is smaller than the protein extent. Why? Okay, let's go with a larger thing. See if there is a fix here that I'm something that I'm missing. Yeah, maybe I should have been following the numbers more precisely. I wanted to make it a little bit faster, but I think I need to go back to. Let's do that. Let's go back to the original details of the tutorial. Okay, so bear with me one more time. So let me see. So in the PC,
Mariano,
yeah.
Can you hear me? I think in the tutorial it writes that you have to put the length of X and Y as 135, not 100. Maybe this resolves the problem.
Oh, okay, thanks. Yeah, I missed that part. But anyway, let's do that the way it's done in the tutorial so that I can try to blame the people that did the tutorial if I cannot get it. So let's go back to cariolipine. So cariolipine PBCl2, so lower leaflet here is 2. Okay, and upper leaflet ratio 0. Then in bacterial, I'm gonna go with lower leaflet of PMPE as 8, and this one 1, PBP 8, and 2. So those are the ones. And where did you find the okay, so one thing that I didn't do is to change the water thickness. Here, the tutorial asks you to change the water thickness from 22.5, which is the default, to 30. Okay, that's good. And let me see if I can find the length of X. Okay. It says membrane bully is 2 options. Yeah, that's fine. And maybe I'm missing something because no. Okay, here. So it says here, yeah, 135 in X and Y. That makes sense. All right. So did it work? Yes, it worked. Thank you. So now I have all these lipids the same way in the tutorial. I was going a little bit ahead of myself, but now we have it here. Okay. And then one thing that it might be kind of like a black box at this point is how can you, if you imagine you can create a membrane, which is going to be a patch, and then wherever the protein is seated, you need to remove the lipids that are there. Okay, so there are no clashes. And that is done in basically automatically. It's designed to be that way. You don't need to learn about it, but you need to know that if you're not using this type of tool and you do it yourself, you need to be careful that when you embed your protein into the membrane, you are able to remove everything that is clashing with your protein. Okay. All right, and then you can choose, while we wait, you can choose the solution that you want to, the salt that you want to neutralize your system. Remember when we did that in QuickND, you were able to also select the concentration of the medium and the species that you want. In this case, it says that the neutralizing species we want is potassium chloride, and then it says that to use some magnesium also for both the lipid A, because some of the lipids may be charged, and so therefore you need some counter ions to balance the charge. Remember, the neutralization is an important process, because if your system is charged at the end of the day, it's gonna give you some bad time. It's gonna, I mean, the simulation could run in principle, but it's gonna give you some errors. Okay, so any questions while we wait for Changui? No questions? Okay, so let me switch gears, because this is taking a little bit of time. That's something that I mentioned earlier. That's that Changui is very powerful, but it takes some time to show. So let me switch to analyze the. So basically, let's take a look at what was at what we obtained from Changui, because I have the files already. I downloaded the files here. So if you go to the files here in the folder, what we get is a series of steps. So basically, Changui prepares a series of steps that you need to run in sequential order. And basically, those are like different type of equilibrations. So for example, it gives us a PDF and a PSF and a PDB for our system. And then the files are basically a series of equilibrations. Okay, so if you go to the bottom of the first one, we can see that this is one type of equilibration. Okay, it might have some constraints on some of the species. And then, for example, if you go to the fourth step, I believe the fourth step is the proper equilibration. Let's see the end. Yeah, there are no. The fourth step basically is like an additional equilibration, much longer equilibration for 5 million steps. So yeah, this if you go to the tutorial now, at the end of the first section, section 1, you get you download all the files from Changui, and then in the second section is basically all the necessary steps for equilibration. You can look here, for example, in the first step, you melt the lipid tails in the first step by and applying some constraints to probably to the protein. Sometimes you want to relax the lipids while keeping the protein fixed, so it's a little bit cheaper the calculation, and also doesn't give any issues with the protein. Then the second, let's see. Yeah, so it's a pretty comprehensive tutorial. Again, I'm not gonna go into every detail, every command, because I think it's we are pressed on time. But yeah, so there is a constraint similar to the constraints that we did during the Tuesday session that were about running a free energy simulation in SMD. And then the second and subsequent steps, it's equilibration with the protein constraint, as I was mentioning. So here you see the intermediate steps. And then this is usually, this is a good, what I like about this tutorial is that it's a very comprehensive step-by-step process that mimics really what you would do in your research. You will prepare your system using CharmGUI, for example, that is very flexible. It has a lot of options. Then you will get results from CharmGUI, and you do these sequential equilibrations where you basically relax things in order, right? First, you relax the lipid tails, then you relax the lipids, then you do relax the protein, and so on and so forth. Okay. For example, here before we did the equilibration with the protein completely constrained, and now we are constraining the backbone, but we allow the side chains to relax, right? And that's the step 3. And then step 4 will be the whole system is equilibrated. There is no constraints in any part of your system. Does it make sense? Okay, so if you're interested in doing simulations of membrane proteins, take a look at this tutorial, and you can basically use this with your own system if you want. Yes, Said, go ahead.
Is there any alternative for CharmGUI to set up a membrane with the protein?
So if there are any other tools different from CharmGUI that
like CharmGUI but not CharmGUI.
I imagine the answer is yes. Maybe Hale and Matt can respond. Maybe you guys have more experience. What I would say is that I think most of the people from our group use CharmGUI at least one time, so to get it one time. And then I was gonna mention that if you have one system created with CharmGUI or any other system, you can generate replicas using other tools. And we have a tool that has been developed recently that is called Membrane Mixer. I have it here. And while it loads. So this plugin it's been developed by one of our grad students, Zepper, and it's in the latest BMD version that you may all have. And what it does is basically once you have a one membrane system or membrane with the protein, you can generate other ones where the lipids are basically shuffled. Okay, so they are change positions, and that might be important because when you do your research, usually you want to have you want to run many copies of your system to get more statistics and to get to validate your results. Because if you only run one copy of your system and you get a phenomenon, you see a phenomenon occur, you don't know if that's like really something that it has merit or not. Okay, so usually most of the people that do this type of simulations, they do multiple copies, and the copies needs to be somewhat different. If you just simulate the same thing 4 times, you're gonna get probably the same results 4 times, even though there is some noise due to the thermostat. You want to have basically your protein in 4 different membranes with the same composition, but with different orientation of the lipids. Does that make sense? So this is a tool that I recommend for basically shuffling and creating more copies of your thing. And basically what it does is it gives you the same quality of a membrane system that you will get from GUI, but it's much faster. Okay, but other than that, I'm not familiar with any other comprehensive tool like GUI. I don't know, Matt, Ale, if you guys have any suggestions.
I've built a couple systems just like myself, but I don't know of any other tools besides GUI. And
yeah,
building it yourself is faster in theory, but I find that oftentimes I forget about certain steps, or I have to troubleshoot each specific system if I'm trying to build it myself. In GUI, it really rarely messes that up in a way that I myself mess it up frequently. So I prefer to use GUI even if it's slower.
yes. Yeah, of course, this is done. I mean, before GUI or before any other tools like QuickND, you need to do this by hand. And what it means is that like you need to get the PDB of your protein and create your membrane, and then put them together and merge them. And some of the tools that are used for that in BMD include like PSFGen and some calculation that you do in your scripts, but that's prone to a lot of errors, and it's not very reproducible either because you need to keep track of everything that you did. And I sincerely recommend GUI for anyone that wants to do anyone that is learning how to do this type of simulations, I would say. Yeah. Okay, so we have a little bit of time in this first session, and we can do different things. So we can go over a tutorial for setting up a simulation, hybrid QMMM simulation. There is a tutorial on our website. If you search for, let me search for the QMMM, and so this is what Rafael discussed earlier today in the morning session. There is quite a good explanation here of all the ideas behind this, all the keywords here, and there is a section with a two type of tutorial. One that it's like a basic tutorial here, and then there is another a little bit more advanced tutorial which includes free energy. But what I wanted to show is that you can prepare your simulations, your QMMM simulations using QuickND. And if you were able to follow along the QuickND tutorial on Monday, it solves a lot of problems for setting up simulations. The same way GUI does for membrane system. This is like a lot of work to do, and this is a good automated way of doing this work. So for the QMMM, you can imagine that most of the important things that you need to set up are defining which atoms are treated quantum mechanically, and of course, if some of the atoms are bonded, covalently bonded to the classical part, you need to set up these link atoms, fictitious link atoms between these two regions, and that is done all by QuickND. So this is a rather short tutorial. It only has like I think 15 pages, maybe even less, 10 pages, and maybe we can go over together. Let me jump to, okay, so this is the QuickND interface that we already discussed earlier this week. Let me load QuickND so I can show you. Okay. So yeah, let's do simulation QuickND. All right. And So it asks us to load this PDB, which is already in the database. So we can do 4P9F. All right. So as I showed earlier, sorry if the resolution is a little bit complicated. It renames some of the residues that are from the PDB to the let me put the white background, maybe that's better, to the force field, to the res names to the force field. And okay, so the next thing it says here is that it wants to unselect the protein it says okay, so it says here we will only use one of the protein chains displayed in the X-ray structure. So our system will only contain one protein chain and one calcium binding site. So it says to remove the B chain, so the B chain for the protein and the B chain of the hetero and the water. The hetero means or hetero means something that is neither some foreign molecule usually is like a drug or something like that. There is neither water nor protein nor nucleic acids. Okay, so this is just the definition inside QuickND. It doesn't have to do anything with the molecule itself. Okay, so if I do that and then I go to structure manipulation, here in the tutorial says that we need to remove, there is some sulfate species that are present from the crystallization of these proteins. So we should remove them here because otherwise we need to add the parameters of the sulfate and maybe those are not in the force field. So if we are, in this case, we are not interested in actually in simulating the sulfate itself. So let's remove that, clicking delete this one. Okay, did it work? Apply. All right. So we click delete and in the SO4, which is the sulfate, and then it says that the residue 153 we need to have it as calcium, but it's already as calcium, so it's already renamed. This tutorial has been superseded by the QuickND updates. Okay, so we just click on check, and it's gonna give us the green light because we basically remove the species that where we didn't have parameters. So now everything has parameters, everything that is here. And that's okay. So the next step is basically the main difference between what we did on Monday and today is that when we go to we need to go to advanced run because QMMM is one of the advanced runs here. So in advanced run, we can set up simulations for the steer molecular dynamics, SMD. We can do MDFF, which is flexible fitting. If we have a cryo-EM density map, we can fit our molecule to that map. So, but now today we want to do the hybrid QMMM. So if we go to the protocol, it gives us some standard protocol, meaning that the same way, remember when I was discussing the charm GUI, that it gave us a series of steps where we were equilibrating progressively our system. So this is the way you usually run your protocol for your simulations. You first start with a minimization, and then you do a process called annealing, which is basically raising your temperature from 0 to your temperature of interest. And then once you finish that annealing, you run an equilibration, and then you run your production, okay? So basically, QuickND prepares the protocol for your setup, for whatever simulation you want to do, okay? It gives you like tentative instructions how to do this. And everything here is run with the QMMM. So we could, in principle, remove some of these steps. Let's say if I already have my system equilibrated, I don't want to run the equilibration, I can click here and remove this. Here in the tutorial, it says that that I don't want to run this MD step because it's a long, kind of like a long step. And also, sorry. Okay, so in here actually what it's doing, what it's doing is running a regular MD, okay, without having any QMMM, right? Because since we are starting from a protein structure from the crystallographic positions, we need to do some equilibration and some minimization, equilibration, and so on and so forth. So basically, you first run a regular classical simulation, and then if you get the results from your equilibration, then you can apply this QMMM setup. So you get for your production simulation, you get the QMMM. So let's skip this part, which is basically the preparation of the classical simulation. And then if you go to the QMMM part, the important part or the important definitions are here in this section called regions. So what you do is basically you both need to define the atoms that are present in the QM and any type of options that you want for your calculation in QM. So the first part is the regions. So you click here in plus, and you add one region, and then you can edit here by basically you have this menu popping up, and you can select any residue that you want in the QM, or if you type here the selection, the atom selection, you can select any type of selection given by BMD language. Okay, so in this case, we are gonna do. Let's see what is the region here. Here in the QM region selection, we have the option to change the number of water molecules. Sometimes you're interested in the interaction with the solvent. So specific water molecules are part of your QM region, your quantum mechanical, treated quantum mechanically. So, and then what it says here is that we need to have the calcium in our, let me change this to 5, sorry. 5 angstroms. The calcium and yeah. So if you click on the calcium, now the calcium and some water molecules that are around the calcium they are within 5 angstroms of the calcium are gonna be present here. So if you click apply, then you already define. Sorry, you already define the atoms that you want, and then you need to change the charge if necessary. In this case, since we are simulating calcium in a water, we need to change that to the charge that you need. In this case, it didn't update, but you can click here and change the. Okay, this is because I'm skipping some steps, but basically you can define the charge here, or it's going to be defined automatically for your case. And the final thing you need to define is here in the options. You can define the options for each part of the protocol or for every step of the protocol. And basically the options that you need to define is which software you want to run your QM simulation. Rafael mentioned that there are different types of softwares that you can run. For example, in this tutorial, I believe it tells you to run a semi-empirical calculation. So semi-empirical calculation is run with MOPAC. You can do also ORCA, but MOPAC is a little bit easier. In case you don't have your Mopac or Orca software in your path, in your defined path, so you need to specify the path where it is. And then there are other options that are given by the detail here in the explanation of the QMMM. So, for example, type of point charges that you may want to use on and off, and then switching of the charges, the point charge scheme if you want to use something different type of options that are defined here. Okay, and this is the command line that you get, and you can, if you're an expert in Mopac, for example, you can change some of the parameters here, like the cutoff or the basis set or some of the methods. For example, this is PM7 is one of the empirical methods, but you can change that to AM3 or something like that, AM1. There are different methods. And then you just click prepare, and then that will give you the idea. So let's see, let's go back to the tutorial. Yes, so this is the idea of the simulation, that you are simulating calcium and the water molecules, the water and some of the residues that are around. And yeah, and some of the other things that in tutorial, this is the basic tutorial, as I mentioned, are just related to the how to display this in BMD, and you get to get better visualization experience with this. Okay, are there any questions for this? Sorry if I went too fast. No questions? Okay,